It is a pleasure to have Eugene Stepanov today, and he will tell us about reconstructing hidden geometric structures in the data from distance matrices. Thank you. Go ahead.
Okay, so thank you very much, and thank you very much for inviting me. And I hope, well, to be able to tell something, maybe something new, I don't know, but let's say, besides telling something new, I would like also to tell some, well, to speak about also some open questions. And well, if you're interested in, we are quite open to collaboration, would be glad to collaborate on solving those questions. So I would like to speak about the classical learning problem. So let's say this is called learning problem. So the problem you are surely quite well acquainted with. So informally, well, it can be stated like this. Suppose you have some hilly landscape in front of you. So there are some hills or mountains in front of your window. You see them, you observe them, you can just walk there. And I am very far from you, many thousands of kilometers away from you, and you would like to share the information on this landscape with me. So what you are doing, instead of taking pictures and sending me pictures, you decide to do the following thing. You go to walk on this hilly landscape, you take lots of points here, and you measure distances between the points. So this you take the points, I don't know, x1, x2, and so on, and you measure the distances. Well, dij will be the distance between each xi and xj. And while speaking in a quite informal language, you take really a lot of points, so almost densely covering your landscape. And then you send me this enormous distance matrix. So you just sending this to me, so I get this distance matrix. The question is, can I, observing this distance matrix without knowing anything about the space, reconstruct the space? So let me formalize the question. So the question is as follows. So let's say, mathematically speaking, so my hilly landscape will be a metric space. So let's say a metric space, a set X with some distance D. And let me say something more. Well, here I will put, besides the distance, I will put also the measure. So, and also some measure mu. So because everything will depend on how densely you will be putting your points in your metric space. So let's say mu is positive Borel measure. Well, I would just think about a probability measure. So Borel probability measure. And I would think that the support of mu is all the set X. So for simplicity, and well, you have the information, all the information on the set, on the distance, and on the measure. And what you would like to send me? Well, you are choosing, so you take a sufficiently large number k, and you choose the set sigma k in X. So sigma k will have k points. So sigma k will be just x1k, and so on, xkk. And while you measure distances between these points, so distances, well, dijk will be distance between xik and xjk, and you send me this distance matrix. So the questions are, well, how should you choose? And then, well, of course, you increase k. So the k you are taking arbitrarily large, you increase k. And the question is, can you choose those sigma k so that I be able, using only this information about this distance matrix, well, to decipher your message, that is, to get the information about the metric space with the measure. A different question, but well, it's a similar question about a little bit different, stated in a different way, is, well, how you can choose those sigma k so as to make me get the information about your space. So question one is how to choose sigma k. Question two, if it is possible to choose sigma k. So let's say how to reconstruct. So from the distances, how to reconstruct x d u. Well, sometimes, well, especially in applications, this is termed a bit different in a different way. Well, let's say, in particular, it often happens that your set X is in fact embedded somewhere in some target space. So there is an embedding from X to some target space, for instance, in a Euclidean space. And well, you are interested in reconstructing the embedding. So let's say how to reconstruct the embedding. And well, let me say, there is what I would call an almost answer to question one, which, well, if it were an answer, I would say it would answer the question completely. Unfortunately, this is not exactly an answer, or let me say, not exactly the answer to the same question. And second thing, so it doesn't exactly do what I want to do. It does something very similar. And well, the second thing is it's extremely difficult to apply. So let's say, so answer, or let me put in quotation marks, answer one was given by Gromov and later reproved, and by the way, by a much easier proof by Vershik, Anatoly Vershik. The question, the answer is as follows. So let's say, let me state their theorem. So let us consider the set R, the set of all infinite distance matrices. And well, I would like to consider the map from x infinity, which is the infinite product x times x times x. So x times x times etc. So infinitely many times into the set of infinite distance matrices, so that, let's say, psi of the sequence x1 etc xk etc infinite sequence, which is in x infinity, while this so let's say psi sends this to just a distance matrix, the distance from xi to xj, and here ij from 1 to infinity. So this is an R. And well, if you put so if you put in R, for instance, the topology of R n times n, so it's quite a weak topology, this becomes a Borel map. And well, if you put here the measure mu infinity which is the infinite product of the measure mu, etc. And if you call now the mu is the image by psi of this measure mu infinity, so the theorem, well, Gromov and Vershik, is that, well, if you know this measure ni, which is the measure on the infinite distance matrices, it means that you know completely your metric measure space. So let's say ni determines x d mu, well, up to an isometry, of course, isometry preserving the measure mu. Of course, when you have this information, well, you cannot hope to reconstruct your original set. You only have the information on distance matrices. So you actually, if you make some isometry, well, the distance matrices will remain the same. So this is the, well, the principal result. Okay. Now, from the practical point of view, so if you would like to see in this answer, well, a kind of an answer to my original question, I would say that this is the same as, so let's say, equivalently, this is the same as, well, let's say, throwing points on your metric measure space randomly. So what you do, you choose random points, psi1 of omega, psi k of omega, and so on. So those are random elements. So omega is just, well, it's a random event. And those are psi1, psi2, psi k are random elements of your omega, of your set X. So they're all in X. And now you have a random distance matrix. So D of omega is a random distance matrix, infinite one. That is, well, it's distance between psi I of omega, psi j of omega. Ij from 1 to infinity. And while the question is as follows, so let's say if you take those psi1, psi k, so all psi I are IID, so they are independent with the same law, with the law of all psi I, the same one, the measure mu. Then actually, while the law of D of this distance matrix is exactly this measure mu. So if you would like to translate this in a very practical language, suppose you would like to explain this thing to applied mathematicians or to engineers, you say the following, well, to make me get the complete information on your metric measure space, that is on your hilly landscape, what you do, you start throwing randomly triples of points, quadruples of points, quintuples of points, then well, thousands of points, billions of points, and so on. Each time you are throwing, well, a k-tuple of points, you measure the distance matrix. Now you make lots of experience with triples of points, quadruples of points, and so on and so on. And you get the whole statistics on distance matrices of all orders. It's more or less the same as having a statistics on infinite distance matrices. once you have this statistics, so this statistics gives you a complete information on your metric measure space. So you can reconstruct this metric measure space from this statistics. Well, just a remark. Just to remark, what I told you is, well, not exactly the same, but almost the same as, is stated in the theorem of Gromov and Vershik. That is, what I told you now is that you take your random points, psi 1 of omega, etc., up to psi k of omega. So this forms a set, as I called it, sigma k, but now a random set, sigma k of omega. So instead of this set, you take the distance matrix, d distance from psi I of omega to psi j of omega. This is a random distance matrix, but now k by k. So let's say, let me call this dk of omega, this distance matrix. Now lore of this dk, let me call it some Nik, and well, knowing the sequence of all Niks, so knowing, well, let's say Ni1, no, well, Ni2, Ni3, etc., Nik, all the sequence is the same as knowing this measure Ni on the infinite distance matrices. So this is a kind of a randomized procedure. Of course, in practice, it's almost impossible to do this. You need to throw really lots of points, make lots of experiments, and well, at the end, find all the statistics on distance matrices. And this is not exactly the answer to my question, although it is quite similar to an answer. Well, by the way, it's quite similar to the answer to question 1. It doesn't say anything about question 2, that is how to reconstruct. But let's say at least question 1 says, well, you can reconstruct via this randomized procedure. Well, let me give you an answer. Now this is really an answer, number 2, which is almost the same, but now it's really answering my question. It's now a real answer. It's non-randomized. So no randomization. I didn't want any randomization. I just wanted to give you a recipe on how to put your points on your metric space and which matrices to send me, so as so that I be able to get the information about the metric measure space. Well, the answer is as follows. So my recipe is as follows. So you take any sigma k in your X, so with k elements. Each sigma k must have k elements. Well, you take them in such a way that, well, if you consider the empirical measures, mu k, well, defined as follows. Mu k is the number of elements in sigma k intersected with b divided by k. So those are, well, let's say, empirical measures. The people in measure theory will usually like to call it the sums of deltas in the points of sigma k. Well, you have to take sigma k so that those mu k will converge weakly in the sense of measures as k plus infinity to the measure mu. If you are able to do so, so theorem, if you are able to do so, well, once mu k tend to mu, well, then the sequence of distance matrices, Dijk. So this sequence of distance matrices, well, determines, well, let me call it, identifies your metric measure space XDU, again up to an isometry, while preserving the measurement. And well, this is more or less the answer to my first question. But of course, while doing in practice what Gromov and Vershik were suggesting, well, is almost impossible, because you have to have this whole statistics on enormous set of matrices. Here, this is a bit simpler because this is not randomized. You don't have to get, don't have to collect statistics. Anyhow, this is quite complicated. And well, one could ask himself something much easier. For instance, so questions. So, okay, let's say question, just one question. So instead of the matrix, instead of a matrix, distance matrix, well, dk, which is dij, okay, well, ij from 1 to k, I would like to take something simpler. For instance, I would like to take the spectrum, and maybe, well, let's say I would like to take the spectrum. For instance, I would take the sigma, of dk, that is, well, lambda 1 of dk, etc., lambda k. Okay. Question, does this spectrum, so what does the spectrum, what does sigma of dk determine? And well, I found, well, quite a lot of works on this question, also some experimental work. But up to now, well, I don't have any, well, I have never seen any definite reply to this question. For instance, even I have seen some people that this is quite well connected to some problems, some physical problems. And I have seen people from statistical physics, well, making some experimental work on this. They were just testing spectra of distance matrices for concrete, well, metric spaces, in particular for concrete Riemannian manifolds, just to understand what does this spectrum determine. But, well, one has quite a number of examples, especially in graph theory. This is called, well, in the case when your metric space is a graph and your distance is a graph distance, this is, the spectrum is what is called distance spectrum of a graph. And there is a lot of works on distance spectra of graphs. Anyhow, many examples, but by now I know no definite answer. Maybe you know, well, in this case, I would like just to know. For me, this is almost completely open. I have some negative replies and I have some slight positive replies on this question, but, well, for me, this is largely open. Okay.
What's an example of a, Eugene, what's an example of a negative reply related to this question?
For negative replies, I would say, the people in statistical physics were interested whether somehow the information about curvature is encoded in the spectrum. So my answer is no. So you are not able to determine the curvature, well, at least curvature in the Alexander sense of a space from the spectrum.
Do you sort of give an example of two spaces that have the same spectrum but different curvatures, or?
Yeah, you can have an example, I think, or even of 4-point spaces, which well, with negative and with positive curvature.
I see. Thank you.
But the question is quite interesting in itself. What can you determine from the spectrum, or for instance, just from the first eigenvalue? What can you determine? What can you know from this? But now let me say something. Well, this is, well, everything here was, well, I was telling everything in quite a theoretical language, which is well understood by mathematicians, but probably not understood by people doing practical applications. So if you would like to look at papers that people in applications have written, you will see what is called, well, what I would call applicative folklore. So let's say, and well, in applicative folklore, there is a lot of methods. Well, you now find lots of programs, lots of software packages, which, well, do the job I was asking myself of how to do. You know, well, there are lots of methods in what is called now manifold learning that are reconstructing, or aimed at reconstructing the space from well, from the distance matrices. And well, one of those, maybe the oldest one, is what is called MDS. It is called multidimensional scaling. That, well, all of you of course know, because, well, you also have studied a lot this. So what you actually, multidimensional scaling, well, you take, instead of a distance matrix, you take a squared distance matrix. So let's say you take d squared from xi to xj. So from ij from 1 to k. And well, let me call it d squared k. And well, of course, if your points are in a Euclidean space, so if your points are in Euclidean space, that is, let's say your x is just Rn, and your distance is just Euclidean distance, is just xi minus xj modulus, then, well, there is a theorem which justifies this multidimensional scaling. So if you multiply this square distance matrix by a projection to a vector, let's say to a constant vector, let's say with value 1 in all rows, so let's say p d squared p, and multiplied by -1/2, then in this case, this will be a positive definite matrix. And while making Cholesky decomposition of this positive distance matrix, you just reconstruct the points xi, xj, and while if you have lots of points and the distances are Euclidean, you reconstruct your original space if the distances are Euclidean. Now, what's happening if the distance if the distances are not Euclidean? Well, lots of people in applications, they just adapt this method to a non-Euclidean situation without caring too much on well, how it works and what it actually reconstructs. So what they do, they somehow mimic the Cholesky decomposition, but they take only, let's say, of this matrix here, they take only positive eigenvalues and the eigenvectors corresponding only to those positive eigenvalues. And then from those eigenvalues and eigenvectors, they try to reconstruct the embedding of their points into the space, into a finite dimensional space. Now there is something, well, I shouldn't tell you because you also did this work. Well, the question is how this thing is justified. And while we were looking at this, well, from quite an applicative point of view, we were interested, well, we were posed by this question by biologists. This question was posed by biologists who were applying MDS method to their genomic data. And they were applying it just blindly, thinking that the distances were Euclidean. They asked us, well, whether actually this is justified. And we found your work, that is, well, where you have taken as a space so you have taken as X just a unit circumference, while as a distance you have taken D, geodesic distance, and mu, just a uniform measure. And then you made this MDS embedding for, let's say, you distributed K points. Excuse me, oh, there's something. So you distributed K points uniformly along the circumference. So this was your sigma K. This was your sigma K. And while you applied MDS methods to get embedding of this, let's say, well, you calculated geodesic distances between those points. So let's say the distances along the circumference. And you then obtained let's say the embedding of those points, so Fk from sigma k to some R and k. And then you are able to pass to the limit when k goes to infinity. This construction gives you an embedding of your unit circumference. Now, actually, those nk tend to infinity, and this one gives you an embedding into L small 2. And what is interesting is that, well, if you make a simple calculation, so let's say the L2 distance, which is f of x minus f of y, in the sense of L2, in the sense of this Hilbert space, is just a constant, well, squared L2 distance is just constant multiplied by the geodesic distance between x and y. So it means that in the limit, when k is sufficiently large, well, when k goes to infinity, what you get is an Aswad type embedding. So let's say this is Aswad type or snowflake embedding of your unit circumference into a Hilbert space. And actually now we have the whole theory. What we know is that in general, so what happens in the limit you have an operator, let me call it, well, T from L2x mu into itself. This T u of x is just, well, let me call it, well, this is integral over x d squared xy du of y in d mu of y. Then what you do, you multiply this by a projector to the subspace of L2 orthogonal to constants. So you multiply p to this projector from the right and from the left, multiply it by -1/2. And well, let me call this operator k. So with this operator, you will have normally, well, in most cases, let me say, well, under quite non-restrictive conditions about the space X, for instance, when X is just a bounded space, but it's enough, much less, you have infinitely many, accountably many eigenvalues. And let's say for each eigenvalue, you have an eigenfunction. So you can make this sequence of functions orthonormal. So they are, well, let's say you might take ui in L2 x mu to be 1. And question, now an abstract question. Suppose you just know this operator, like it's like saying you know lambda I and ui. So somebody has done this job for you, and he found lambda I and ui. You also know that ui are continuous functions on your space. In this case, this is known. And you also know your set X, for instance. And moreover, you probably know the let's say the topology on your set X. So you know that your functions are, your ui are continuous. So question, can one reconstruct? Does this determine, can one reconstruct your x d mu in general? Again, this is, the question comes from the applicative folklore, but well, in the applicative folklore, what people are using, people only use the positive eigenvalues and the eigenfunctions corresponding to positive eigenvalues. And here I'm asking about all the eigenvalues and all the eigenfunctions. Can one reconstruct the x d mu? And again, let's say I would like also to have the complete answer to this question, but I only have the partial answer to this question. So let's say partial answer. So partial answer is as follows. So let's say, if you know the class of equivalent measures, if one knows the class of equivalent measures, say the class of equivalent measures, or which is the same, one knows the ideal of sets of zero measure. So one can then, when reconstructs then the sequence lambda I and ui, so this sequence, so this one, then determines d and mu uniquely, well, with mu in that class. So let's say mu in this given class. But in principle, I don't know what happens. Maybe it is possible to have two different measures. So let's say the same distance, but two different measures, mu1 and mu2, both this with the support, the whole space, but singular, one with respect to another, so mutually singular. And to have the same spectrum and the same set of eigenfunctions of this operator. So the operators will be different, of course, because mu is different. But I don't have a counterexample. Maybe you can have, well, let's say, occasionally you might have some strangely the same spectrum and same eigenfunctions. Just a remark. In any case, well, the knowledge of eigenfunctions of UI with the norm of UI, so let's say not just any eigenfunctions, but eigenfunctions such that they are normed somehow. I need to know how they are normed, say by 1, is important. That is, knowing only eigenspaces plus the spectrum, of course, is not enough. Well, just probably to finish, let me put the, well, let's say, let me restate more or less the same problem. Well, very similar to what I have told, but let's say quite a similar problem. Let's say a very similar question. Well, actually, the two are pretty much related between the two. So let's suppose that, well, you have this metric measure space xd mu. Again, mu is a probability measure with the total support. So as I explained before, and what you do, you are taking those sets sigma k. So let's say in X, say the sigma k each has k points, and well, let's suppose for simplicity, you can also suppose that the sequence of sets is just increasing. That is, sigma 2 is subset of sigma 3, is subset of sigma 4, and so on. This is subset of sigma k, and so on. And for each set, you make this matrix. Well, let's speak about not about the distance matrix, but about the squared distance matrix. So d squared k will be just the squared distance matrix. So dkij squared ij from 1 to k. And let us suppose that, well, each time you are calculating this matrix, well, you are calculating the spectrum. So calculate sigma of dijk. So this will be some lambda dij, excuse me, dk squared. Yeah, it was called dk squared. So it will be lambda 1, lambda 1 k, etc. lambda kk. What do you know about this sequence? Well, what you know about the sequence is that, well, you have the Cauchy interlace theorem. That is, let's say, the spectrum of corresponding to the k+1 matrix lies in between, in the intervals formed by the spectrum of the case matrix. So this is the Cauchy interlace theorem. What you also know that when your mu k corresponding to sigma k, so let's say those mu k empirical measures, corresponding to sigma k, let us suppose that if they converge weakly to your measure mu, then under quite non-restrictive conditions on your space, well, you can, for instance, they are surely satisfied when your space is bounded, but actually much less is necessary. Well, you can think that those lambda j k, they converge as k goes to infinity to some lambda j. Those are eigenvalues of the operator T, the one coming from the infinite MDS. The question is as follows. So of course, well, if I know all the spectra for each k, or at least for all sufficiently large k, and also all the eigenvectors, then, well, at least using the previous result, I could just, well, knowing the class of measures, I could reconstruct my space. But now I'm again asking the same questions I was asking before. So can one say something about the space knowing these spectra? So knowing this, so let's say, what do they determine? And by the way, it would just be interesting to make examples, And while it seems quite curious to say, well, what is happening is that, well, for instance, one can just think about the signature. Let's say consider the signature of this dk squared. So the signature is, let's say, number of positive and number of negative eigenvalues. What one always has, so let's say, well, this is alpha beta, and one always has that beta is greater or equal than 1, because this is a matrix of positive elements, so because of Perron-Frobenius theorem. And since the diagonal of this matrix is 0 and beta, well, there will be some biggest eigenvalue. One can also have, well, one necessarily has alpha greater or equal than 2. So this is number of negative eigenvalues. And this is number of positive eigenvalues. But it seems that in most examples, when k tends to plus infinity, so this will be alpha k beta k, can tend to plus infinity, then alpha k also tends to plus infinity. Unless, of course, you are dealing with a finite metric space. Right? So, okay, dealing with infinite metric space. Well, conjecture 1 for almost every metric measure space xd mu, and there are many ways of saying almost every. If you ask me, I could just tell you something. There are many ways of telling this. For almost every xd mu, alpha k will tend to plus infinity. The conjecture or question, I'll say question question 2. Can one have alpha k is equal to 2 for every k? Or
Eugene,
yeah,
how many more minutes?
I think that, well, I would stop here.
Okay.
I would just say that even with, if you are dealing with non-distance matrices, but just with positive matrices, with positive entries, with zeros on a diagonal, making this example is quite difficult.
Yeah.
For distance matrices, for square distance matrices, I don't even know how to do this. So let me just finish here.
Okay, thank you. And I suggest we unmute ourselves and thank Eugene for today's wonderful talk. Okay, any questions?
I have a couple of questions. Unfortunately my Wi-Fi got out for a bit, so I got kicked off. So I'll have to watch the recording for the last couple of minutes. But so you had this result, this partial result, that if you know the equivalent measures, then you can determine the distance, etc. So so you sort of described that it's not known what the classes of equivalent measures are, but is it correct to say that if two measures are equivalent, then one's singular with respect to the other?
No, by equivalent measures, I mean that, well, let's say each one is absolutely continuous with respect to the other one.
Right.
So they share the same ideal of sets of zero measure.
Right,
The sets of zero measure are the same for both measures. So once you prescribe the ideal of sets of zero measure, this determines the class of measures. Within this class of measures, you reconstruct your measure. Yeah.
I see. Okay, and then you don't know if it's possible.
And in general, I don't know. Well,
two measures with different notions of sets of zero.
Yeah.
But it's sort of an exotic counterexample if it exists. Okay.
But let's say I would just stress these two last questions, conjecture and question. That is, can you think about an infinite metric space? Let's say an infinite metric space, such that you take triples, quadruples, quintuples of points and so on, consider the square distance matrix, and the number of negative eigenvalues is always 2. The number of positive eigenvalues grows. And conjecture 1, I'm quite sure that this is true, that for almost every metric measure space, you will have, let's say, infinitely, in the limit, you will have infinitely many negative eigenvalues, which, by the way, if you think about this, your infinite MDS, in infinite MDS, those negative eigenvalues become positive eigenvalues because you multiply by -1/2. So it means that your negative MDS is, let's say, almost never void. Let's say you will have infinitely many positive eigenvalues. You know, you will always have at least 2, but or at least 1, because, well, you use those projectors. The question is, well, can you show this rigorously that for almost every, you of course have to discuss what is almost every. Because there is one more curious thing. In a certain sense, almost every metric space, if you forget about the measure, almost every metric space is a Urysohn universal space. in the following sense. If you go back to, well, the construction, well, so you have this space of infinite distance matrices. So this set of distance matrices corresponding to corresponding to various dense subsets of a Urysohn universal space is a G delta dense set in R. Well, saying in simple words, well, let's say almost every, in the sense of category theory, almost every metric space, without thinking about measure, is the Urysohn universal space. Which means that if you are not thinking about measure, you make some small errors in your measurements, well, most probably you will reconstruct the Urysohn universal space or its subset if you are speaking about just finite sigma k. Just maybe to mention something. Well, the questions I posed are also interesting for classes, for subclasses of metric measure spaces. For instance, for Riemannian manifolds. The last questions are quite interesting. For instance, can you say that, well, question 2, that this cannot happen for a Riemannian manifold? For a smooth Riemannian manifold. So this one should be probably quite exceptional. I think that it is impossible to have this for a smooth Riemannian manifold, but, well, no counterexample for the moment.
Okay, I have a question too. So I'm actually interested in the effect of MDS on the topology of original space. We know that if we apply MDS to n sphere, the resulting space is actually homeomorphic to Sn itself, even though the metric becomes different, the metric becomes Euclidean. But I'm wondering what happens if I apply MDS to more, I don't want to say strange, but more complicated space such as Klein-Bodel or projective spaces. Will we have some homomorphism between the resulting space and the input space, or at least homotopy equivalent? Do you know anything about that?
Let me give you maybe 2 answers. Maybe one is enough. Well, answer 1, I don't know. And I would be interested to know. It looks like that in most cases you will have a homomorphism, but it is very, very much related to the thing I told you, by the way. Well, to the thing I told you about just a moment, about, well, about the reconstruction. So let's say, is it possible to reconstruct knowing the eigenvalues and eigenfunctions of the limit operator? Is it possible to reconstruct a metric and a measure? Why I'm saying I'm only able to prove this when I know the class of equivalent measures. This is just the same obstacle you have when trying to prove that your knowing, well, that actually you have a homomorphism.
Mhm.
Because what you prove is that this is in a sense an almost homomorphism. So let's say almost every couple, well, preserves the distance in a certain sense,
Mhm.
preserve the squared distance, something like this. And you know this, but from almost where every going to every, there is a problem.
Mhm.
And this is exactly the same problem you have here.
Yeah. Mhm. Yeah. Yeah. Okay.
There are some other examples in which you have a homomorphism still.
Sure. Sure. Yeah. Other than a sphere. Yeah. Okay. Thanks. Maybe one more question, one last question, if we have.
Mhm.
Okay. If not, let me stop the recording. And thanks again, Eugene. It was nice talk.
Again, thank you very much for inviting me.